Okay, so I hope you can hear me. So welcome to the week 9 assignment solution for the course Bonds and Bands and Solids. So today we'll be solving our assignment 9 whose problems are as follows. So the first problem is that the asymptotic form of the radial wave function used to calculate the charge density due to the impurity at large distances is given by. Now this asymptotic form is form like one can consider and can start with the charge density due to these impurity, and let's say these impurities are present at large distances from each other. So the charge density at say point R from the impurity would be summation of all the occupied states times the probability square. Now asymptotic form of the wave function in this scenario would be given by, write it down, K and L. Eta L are the phase shifts in the radial wave function, 2 pi R, so KR minus L by 2 plus eta L divided by R. So this formation is the asymptotic form, and it in current option matches with option number 5, because in all other options with the term L pi by 2 is in plus sign here, which is not correct, and it would be the correct option would be option number 5. And the next question is, which of the following statements is true for Friedel oscillations in metal? So one can write down this expression where that the delta of the change in charge density due to these impurities can be written as 2e divided by pi square summation over L. L is the angular momentum quantum number, minus 1 raised to the power L sine of the phase shift times 1 by R cube multiplied by cosine of 2kf. Kf is the Fermi vector, R plus eta L. Now this whole term is a constant, and so one can see that the charge density varies as a cosine function, and cosine function has distance in it. So charge density, since cosine function is an oscillating function, so with distance, or I can say with increase in distance, one can expect an oscillatory cosine behavior, and this oscillatory behavior is nothing but the Friedel oscillations in the metal. So the charge densities show oscillatory behavior with distance from the impurity, so correct option would be option number 3. Now the question number 3 says, which one of the following is the Lindhard expression for dielectric constant? Now this expression for Lindhard's expression for dielectric constant comes from a rigorous theory where the epsilon, which is a function of the wave vector, the perturbation wave vector q, and frequency, and q is a vector, so I'll put the vector sign, is equal to 1 plus 4 pi e square by q square, where q is again the wave vector, summation of all the k states. F naughts are the Fermi function at k, and the difference in Fermi functions at k and k plus q, divided by energies at corresponding to k plus q minus energy corresponding to k, which is nothing but h cos k square by 2m, minus h bar omega plus I alpha, where alpha is a small positive constant. So this expression, the Lindhard expression, is a generalized expression which reduces down to Druder's model if one simplifies and considers all the Druder's assumptions. So which means that this expression is in general form correct. So this expression right here matches well with it matches correctly with only one option here, which is we can see now this can be also seen directly from the coefficient, that is the potential form given to us 4 pi e square by q square, which is only available in the first option. So eq omega in the Linhart expression is 1 plus 4 pi e square by q square, and summation goes as follows. The next question is the form of the screen Coulomb potential in a metal is given by. Now in general, this Coulomb potential, this potential varies inversely with R. But in case of metals, due to this Thomas Fermi screening, there is an additional term that decays this potential, and that additional term is an exponential term. So potential varies 1 by R, and also there is an exponential term, let's say constant to be lambda. Now this exponential term, what it does to the system is, in general it should have gone like this. If I say that this way is the potential energy and this way is R, so if R decreases, potential energy becomes negative. Okay, but in case of metals, due to this presence of exponential function, potential energy behaves as follows. So due to this screening, the potential dies very fast, and therefore the correct option given to us would be exponential with a negative lambda r, where lambda, in fact inverse of lambda, is called the screening length. Or Thomas Fermi screening length. So the potential, the form of the screen Coulomb potential would be e square by r into exponential e to the power minus lambda, where lambda is the screening length. Now question number 5 says the relationship between the static dielectric constant, static means that frequency omega is equal to 0, there is no frequency variation, and the inverse screening length, since 1 by lambda is the screening length as we discussed earlier, so lambda would be inverse screening length. Now in the Linhart expression that we found earlier, where epsilon k comma q, where k is the perturbation vector, is given by 1 plus 4 pi e square by q square, summation over all k, and we have let me just find it very quickly. F naught k are the Fermi functions corresponding to k plus q divided by energies at k minus ek k plus q h bar omega minus I alpha. Now in the earlier formulation we had now there might be a correction here, that f naught k is the first term in the numerator, and k epsilon k plus q is in the denominator. So in fact these terms should be equal, so epsilon k should be the first term, and then epsilon k plus q. So let me just correct it down. This would be minus plus, and these two terms would remain as it is. So one has to maintain the consistency in the numerator and the denominator both. In fact, in the previous one, one would expect, just a second, one would expect a positive h bar omega and minus of alpha, but due to I think the misprint in the solutions, but the option will still be A because of the prefactor is given wrong in all the three options. So 4 pi e square by q square, option A will still be the solution, but there is a small correction that epsilon k would be coming in front, and rest of the term will modify. So now in this one, when one puts omega equal to 0, we would have our static dielectric constant, and the expression for the Linhart dielectric constant would modify subsequently, where the summation changes to an integration, and the terms inside this summation, the difference between the Fermi function at k and k plus q, and in the denominator the difference between the energies and k and k plus q, modify down to, I'll write the final expression, to derivative of the Fermi function with respect to energy multiplied by the density of states at E and dE. So then the summation in K has been transferred to, has been transformed to integration in E. Now this term in the brackets along with the total integration can be written down as the density of states at Fermi level, because NET is the density of states which varies with E, whereas del EF by del E naught only survives when E is equal to EF. So the summation of this, the integral of this product survives only at E is equal to EF, and which gives us density of states at EF, which I can call as N of EF, or I can say N of EF. So 1 plus 4 pi e square divided by q square, density of states at Fermi level. Now this total term in the numerator, one can call it as lambda. Let us term it as lambda divided by q square. So this expression of static dielectric constant expression, and this is the option given to us, is 1 plus lambda square divided by q square. Option C would be the correct option for the static dielectric constant. Just to keep in mind that the lambda which we have just supposed here, lambda square is 4 pi e square times n varying at density of states at Fermi level, is given by this expression. Now if one takes lambda would be square root of 4 pi e square n of EF, and just as we learned just before that, 1 by lambda is actually the screening length. So 1 by lambda would be 1 divided by 4 pi e square n times density of states at Fermi level. Now in the next question number 6, it says that if the density of states at Fermi energy is n of EF, which we have already know, then the screening length in the CGS unit is given by, screening length means 1 by lambda, is given by 1 divided by 4 pi epsilon naught square n of EF. So the option would be 1 divided by 4 pi n of EF. But when now question number 7 says that at low temperature, if the density of states of the Fermi level is n of EF, then the screening length, now in SI unit, the term just find it out quickly. Yes. Now when you convert from CGS to SI, one over 4 pi transforms to epsilon naught, and the rest of the units, and keeping the rest units in mind. So our expression for Fermi screening length, that is 1 by lambda, which we know in a CGS system as 4 pi e square n of EF, E of F, becomes epsilon naught divided by the square root divided by e square n of EF, combining the two square roots in numerator and denominator, we have n of EF. So the correct option becomes option number B, epsilon naught divided by E square n of EF. So screen length in SI units is given by epsilon naught divided by E square n EF all the whole square root. Now the question number 8 says that the number density of conduction electron in copper N is given by 8.47 into 10 to the power 22 centimeter cube, or I can say in SI units, since we are more easy conversion in SI units, becomes 10 to the power 8 meter cube. And lambda square can be written as 3, and since we are to find the screen length of copper, so we are bound to find 1 by lambda, and there's an expression for screen length which relates to the number density of electrons, in the sense that n 1 by 3 multiplied by mass of electron times charge square, n is the conduction electron density, divided by epsilon naught h cross square pi raised to the power 4 by 3. Now this expression can be modified to the expression as 4 multiplied by 3 by pi raised to the power 1 by 3 and multiplied by n raised to the power 1 by 3 into a naught, where a naught is the Bohr radius. So this expression is given in Kittel in chapter 14, plasmons, polaritons and polarons, and in the edition which I am working on, it is on page number 405. But let us stick to the basic expression, and we will see that where we'll end up. So I'll take a separate page to do the calculation explicitly right away. So let us find out these values. So 3 raised to the power 1 by 3, if one evaluates it, turns out to be 1.442 multiplied by mass of electron 9.1 into 10 to the power minus 31 kg. 1.6 into 10 to the power minus 19 is the charge on electron square, multiplied by n given to us is 8.47 multiplied by 10 to the power 28 raised to the power 1 by 3. Okay, divided by epsilon naught, the permittivity of the free space value is 8.85 multiplied by 10 to the power minus 12. H cross one can write as h by 2 pi square into pi is 3. Now if we evaluate pi raised to the power 4 by 3, it comes out to be 4.601. So 1.442, 9 and 1.6 square when collected together counts to 33.592. The 10 is the power of the mass from the mass of electron. Now 10 to the minus 38 comes from the square of the charge of electron, and inside the bracket we can transfer 110 to 84 point, becomes 84.7, and it becomes 10 is the power 27 raised to the power 1 by 3, and rest we have with us as 8.85 multiplied by 10 to the power minus 12. Now h is 6.626 multiplied by 10 to the power minus 34 square, and the bottom 4 pi square that is here goes into the numerator, becomes 4, and pi square is nothing but 9.869. We have accounted for that, and this becomes 4.6, stays as 4.601. So collecting the powers of 10 together, we have 10 to the minus 31 and minus 38 gives us 10 to the minus 69, and 10 to the power 27 raised to the power 1 by 3 gives us plus of 10 to the power 9 divided by minus 12, and this becomes minus 68, and minus 12 becomes 10 to the minus 80, and rest of the terms in numerator we can separate out. Multiplied by 84.7 raised to the power 1 by 3 comes out to be 4.391 divided by 8.85 into 43.90 would be the square of 6.626 multiplied by 4.601. So this 10 to the minus 80 goes into the numerator, becomes 10 to the plus 80, plus 80 and 989, and 69 becomes 10 to the power 20. And if one evaluates this expression, we are left with 3.25. So lambda square thus becomes this. Taking square root gives us 1.80 into 10 to the power 10, and 1 by lambda is the screening length, gives us 1 divided by 1.8 into 10 to the minus 10. 1 by 1.8 nothing but 0.55 into 10 to the minus 10 meters, or 0.55 angstrom. So the correct option, given that conduction electron density on copper is screening length, becomes 0.55 angstrom. So question number 9 we are with now, which says that the origin of conservation of crystal momentum. Now, the origin of conservation of crystal momentum comes from the translational invariance present in the material, or let's say all the Newtonian mechanics is in Newtonian mechanics momentum is conserved because physics does not change if we move the object from one place to another, and similarly this can be argued that conservation of angular crystal momentum inside the crystal is because of the translational symmetry. Now question number 10 says that if a and b are complex numbers and phi1 and phi2 are two functions, which of the following is true for an antilinear operator? Now in general, for a linear operator, let's say if a function f, if f is a linear operator, then if I say f operates on a of phi1 plus b of phi2, it gives us first it works on in the individual sum. That is the definition of the linear operator. And if a and b are constants or complex number, but a linear operator only works on the function and takes out a as it is outside and works on phi1 plus b times f of phi2. But by definition, the antilinear operator and in this case antilinear operator is given as t. Now in case of antilinear operator, if we have the similar scenario, it works as individually on the two functions, but it works on complex number in the sense it transforms them to their conjugate, t working on phi1 plus b conjugate and t working on phi2, or one can put a bracket. So this is the definition of an antilinear operator, and by this definition the correct option given to us is option number B, where a star t working on phi1, b star t works on phi2. Now this t, which was antilinear operator in this earlier question, is actually the time reversal operator in quantum mechanics which you deal with. And this, if t is a time reversal operator and provided us that crystal Hamiltonian H has time reversal symmetry and t is a time reversal operator, then by definition t works on crystal Hamiltonian, where T dagger is nothing but the Hermitian conjugate of T, should be H. So if this condition is satisfied, then T becomes a time reversal operator for Hamiltonian H, and this current option is given to us as option number 4, where T dagger is equal to the Hamiltonian again. Now question number 12 deals with the application of this time reversal operator. It says that if K is the complex conjugation operator and the sigma I are the polyspin matrices, we can write T as U times K, where K is the complex conjugation operator and U is a unitary matrix. So, and sigma I are the polyspin matrices. The time reversal operator T for even number of spin half particles 2n. Now it is given to us as particles are given as 2n is given by. Now one can try to approach this problem as follows. The time reversal operator in case of polyspin matrices, which are these unitary matrices, can be written as T is minus I K, that is a complex conjugation operator, and sigma Y I is the polyspin matrices in Y along the Y direction. So for even number of spin half particles, one has to take the product of all these. So cumulative product, which runs from let's say J from 1 to n, and n is here is 2n. So what would I do here is minus K kappa sigma Y, and we are left with this. Let's say n is even, so n can be taken as 2n. Now if one does it, but we are left with minus I iota raised to the power n kappa raised to the power n, the product of all these matrices now k raised to power n, and this all the product that runs along all the j's is a product of all these unity matrices, nothing but again sigma Y. So but in case of spin even number of spin half particles, but we are here with, now this becomes the T for all the particles. Now if one considers n to be even, then n to be even and 2n, so we are left with T. Let me just ponder it over a second. Then n for sure iota goes to 1 because n is even here in the multiple of 2, and T, the translation operator, remains K raised to power 2n. Just a second, there might be a slight miscalculation, I think. If we T is equal to K raised to power 2n, shouldn't be now. I think, yeah, when K raised to the power even times 2 and it becomes 1, and the sigma Y's are also becomes 1. Finally what would be having is in t, this initial iota part was 1, so we left with t will be 1.
Hello.
Hello.
Yeah, I checked this t equal to 1, but in the result it shows that it's a wrong answer.
Yeah,
And
it shows t as -1 raised to power n.
yeah.
Okay, okay. But in that case it would still be correct, because in the sense that we have even number of particles, and at the end of the day, if one raise n to be even here, then it would give us 1. So
But 1 is also correct.
yeah, 1 is also correct. Yeah,
I
so
don't know, the next one was also, written in generalized form,
uh-huh,
maybe.
yeah. So one can always I mean, one should not do in principle, but at the end of the day, what we will be studying as I as minus I, or -1 is power n to be, if n is odd, as -1. So that is correct. That would be correct.
Okay.
Okay. And then, and in the same case, if k is the complex conjugation operator sigma I, and in the case of odd number of particles, this uh, the t that we just evaluated above as -1 raised to power n minus I iota raised to power n kappa n sigma y. Now if n becomes 2n plus 1, then what we are left with is, now if n is odd, iota is a minus of iota of 2n plus 1 becomes minus of iota, and k raised to the power 2n plus 1, the complex conjugate operator, still gives us finally k, because k raised to the power 2n was 1, and k raised to the power 2n plus 1, that is multiply one more time by k, gives k, and sigma y raised to the power 2n plus 1 times in the above pi product gives sigma y as it is. So in this case,
Well, same here. That -1 to the power n I was ticked as correct answer, but I written this minus I k sigma y, then it was marked. Wrong,
okay. um,
because these two are similar. So if one is wrong, then other is in the same result. Maybe.
yes,
Yeah.
yes, but since I do not know how that particular uh, the answers are written in this form, but the correct option are these things.
Yeah. These two are. I never will go wrong, but today. So saw that the answers are maybe they wanted the generalized answer, so they take those -1 to the power n. But it actually simplifies to the shorter form.
Yes, this goes directly in this if one puts the value of n. But I think this one can defend that this is the perfect answer, but in the generalized expression, -1 raised to
Yeah.
power n does not give that much of a wrong answer.
Mhm. Okay.
Okay. Now the question number 14th we have, which says that um, which one of the following statements is true for time reversal symmetry? Now in the case of time reversal symmetry, this time reversal, if one does the calculation, this time reversal symmetry now what it does, it imposes degeneracy. One has to minimum of two-fold degeneracy for odd number of particles, uh, two-fold degeneracy between the states of opposite momenta and opposite spin. Because when time reverses, say let's say one particle has momentum L it becomes minus of L if one reverses the trajectory and the spin momentum. So the degeneracy comes between these two states of momentum, and same with the opposite spin. Now, so it imposes degeneracy between states of opposite momenta and of opposite spin. Now, as we have just seen, the condition for a system to have at least twofold degeneracy is that system should have odd number of electrons and time reversal symmetry. So this is directly a result of the time reversal symmetry, that it should have odd number of electrons and time reversal symmetry. And finally, we have our spin orbit interaction, which we have a few postulates with us. Lifts the time reversal invariance of the Hamiltonian, retains the time reversal invariance. Now, in the absence of the external magnetic field, L becomes minus of L in by time reversal symmetry, and S becomes minus S. But in the case of magnetic fields, the states split up and the time reversal invariance is no more. So a spin orbit interaction retains the time reversal invariance of the Hamiltonian in the absence of external magnetic field. So the correct option would be option number B. And with this we have completed the assignment 9. And if there are some questions, we can answer it, or we can close the session. Okay, if
it's okay.
Okay, if there are no more questions, then I'll close the session and we'll meet next time. Thank you.